Formal definition of conditional probability. Welcome, everyone. Before we dive into the new material, let's take a moment to reflect on what we have already covered. In our previous lesson, we explored the intuitive concept of a reduced sample space. We discussed how, when we receive new information, specifically, when we are told that a certain event has already taken place, our entire perspective of the total possible outcomes shifts. We are no longer looking at the original, broad universe of possibilities, but rather a smaller, more specific subset. Today, we are going to take that intuitive understanding and move beyond just feeling how it works. We are going to formalize that intuition into a precise, mathematical definition that you can use to solve complex probability problems. Understanding the notation. In probability, when we want to express the likelihood of an event E occurring, specifically under the condition that another event F has already taken place, we use a very specific notation. We write this as P of E given F. Notice that vertical bar in the middle? That bar is the key. When you see this, you should always read it aloud as the probability of event E given event F. To make sure we are using this correctly, let's break down the components of this expression. The first part, E, represents the specific event whose probability we are trying to calculate. The second part, F, represents our condition. It is the event that we already know has happened, which effectively shrinks our focus. As we will see in the next slide, understanding this distinction is crucial for deriving the actual formula we'll be using to solve problems. Now that we have the intuitive idea of a reduced sample space from our previous discussion, let's move on to slide 2 to learn how we actually write this down in mathematics. Deriving the formula. Now that we understand the notation and what it means for one event to be given another, let's move on to the most important part, how we actually calculate this. On this slide, we're going to derive the formula for conditional probability. There are two different ways to look at this, and both will lead us to the same result. First, we'll use the classical approach, which is based on counting outcomes, and then we'll use a more general approach based on probability values. Let's start with approach A, which uses the number of elementary events. Think back to our first slide where we talked about a reduced sample space. If we assume all outcomes in our original sample space, let's call it S, are equally likely, and we are told that event F has already happened, then event F effectively becomes our new, smaller world, our new sample space. Because of this, the total number of possible outcomes is no longer the size of S, but rather the number of outcomes in F, which we write as N of F. Now, for event E to actually occur within this new world, the outcome must satisfy two conditions. It must be part of event E, and it must also be part of event F in mathematics. We call this the intersection of the two events. Written as E intersection F, so the number of favorable outcomes is simply the number of elements in that intersection. Or N of E intersection F. When we put this into a fraction, we get our first version of the formula. The probability of E given F equals N of E intersection F, divided by N of F. Now, if you prefer working with probabilities rather than counting individual outcomes, we can use approach B. This is a clever algebraic trick to turn our counting formula into a general probability formula. We are going to take our fraction and divide both the top and the bottom by the total number of outcomes in the original sample space, which we call N of S. If we look at the numerator, N of E intersection F divided by N of S, that is exactly the definition of the probability of E intersection F. Similarly, the denominator, N of F divided by N of S, is the definition of the probability of F. When we substitute these back in, we arrive at the formal, standard definition. The probability of E given F equals the probability of E intersection F, divided by the probability of F. However, there is one vital rule you must remember. This formula is only valid if the probability of F is not equal to 0. If the probability of F is 0, it means event F can never happen in the first place, which would make our division impossible and our conditional probability undefined. Keep this in mind as we move into our next slide to see this formula in action with a real-world example. Real-world example. Now that we have derived the formal formula, let's put it into practice with a real-world scenario to see how this reduced sample space we discussed earlier actually works in a calculation. Imagine we have a class of 50 students. Within this group, 30 students like mathematics, 20 students like physics, and 10 students like both mathematics and physics. Here is the question. If we pick a student at random, and we are already told that they like mathematics, what is the probability that they also like physics? Let's break this down step by step. In step 1, we need to identify our events clearly. Let's use M to represent the event that a student likes mathematics, and P to represent the event that a student likes physics. Because the problem tells us the student likes mathematics as a known fact, we aren't just looking for any student, we are looking for the probability of physics given mathematics. In mathematical notation, we write this as P of P given M. Moving to step 2, let's list all our known values from the scenario. The total number of students in our original sample space, which we call N of S, is 50. The number of students who like mathematics, N of M, is 30. The number of students who like physics, N of P, is 20. And finally, the number of students in the intersection, N of P intersection M, which represents those who like both, is 10. In step 3, we need to convert these counts into probabilities so we can use the general formula we learned on the previous slide. First, the probability of a student liking mathematics, P of M, is 30 divided by 50, which gives us 0.6. Next, we find the probability of a student liking both subjects, P of P intersection M, which is 10 divided by 50, resulting in 0.2. Finally, in step 4, we apply our formal definition. We take the probability of the intersection and divide it by the probability of the condition. So, P of P given M equals P of P intersection M divided by P of M. Plugging in our numbers, we get 0.2 divided by 0.6. When you simplify that fraction, you get 1 over 3, which is approximately 0.333. To conclude, the probability that a student likes physics, given that we already know they like mathematics, is exactly 1/3. As we move to the next slide, I want you to pay close attention, because there are a few common traps students fall into when interpreting these types of problems. Common mistakes to avoid. First, be very careful not to confuse the probability of E given F with the probability of F given E when you look at the notation. Remember that the event following the vertical bar, which we read as given, is the one that has already occurred. It is the condition that has already been met. As we saw in our previous example with the students, the probability of a student liking physics, given they like mathematics, is not the same as the probability of a student liking mathematics, given they like physics. The order of these events matters immensely. Second, do not confuse the conditional probability, P of E given F, with the intersection, P of E intersection F. This is a very common mistake. The intersection, P of E intersection F, represents the probability that both events happen simultaneously within our original, full sample space. However, conditional probability is different. It is the probability of E happening after we have already restricted our entire world to only the outcomes in event F. In short, the intersection looks at the whole group, while conditional probability looks only at the subgroup. Finally, never forget the mathematical requirement that the probability of F must not be equal to 0. As we mentioned during our derivation of the formula, if the probability of event F is 0, then event F cannot possibly occur. If the condition itself is impossible, the conditional probability becomes mathematically undefined. Now that we have seen how to apply the formula in a practical scenario, I want to pause and highlight some common pitfalls. Even students who understand the concept can easily lose marks by making these 3 specific errors. Keep these distinctions in mind as we move toward our final summary of the key takeaways. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. First, let's revisit the notation. Whenever you see the vertical bar in the expression, the probability of event E given event F remember that the event following that bar, which is event F, is the one we already know has occurred. It is our starting point. Second, if you are working with a scenario where all outcomes are equally likely, you can use the counting formula. In this case, the probability of E given F is equal to the number of outcomes in the intersection of E and F, divided by the number of outcomes in event F. This is essentially just looking at the overlap relative to our new, smaller group. Third, for more general problems where you aren't just counting outcomes, we use the general formula. Here, the probability of E given F is equal to the probability of the intersection of E and F, divided by the probability of event F. Just a quick reminder. This formula only works provided that the probability of event F is not equal to 0. Finally, I want you to remember the core concept behind all of this. Conditional probability is all about a shift in perspective. We are moving from our original large sample space, which we call S, to a reduced sample space, which is event F. We have shrunk our world down to only the outcomes where F is true. If you have reviewed these points and feel confident, you are ready to tackle the exercises. Great job today!